Hey there, everyone. My name is Ryan Schul, and I created this channel called Straight Data Science probably about 9 months ago. And I go through all kinds of different topics, some related to finance. That's what I studied in school, some completely unrelated to finance. And it can be all kinds of different analyses that I do. But I think all of it is practical and useful. And I share my findings with you here. So, the topic that I want to talk about today is New York City subway ridership and how we can do analysis to gain more insights and understand the patterns and the frequencies of people moving around New York City using the subway. So basically, analyzing NYC subway ridership isn't just about counting people on trains. It's really serves a whole bunch of different purposes. Some of them are very critical too, especially for the city making decisions across urban planning, topics like transportation policy, public safety, equity, and even the overall economics of New York City too, right? So there's a few different reasons why we would want to do this type of analysis, probably for urban planning and infrastructure optimization, policy and budget decisions, economic and business impact, emergency response and public safety, overall sustainability and environmental planning, and even equity and accessibility, right? And how do people get around? How do people get from point A to point B? So let me go ahead and kick this off. I found this data set. I think this is going to serve the purpose quite well. I was actually planning to do this type of analysis a while back, like a few months ago, and I looked around for the data. I couldn't find it, so I put this on the back burner. But just recently, I think it was like literally this morning, I found some data that looked pretty useful. So I decided to take my ideas and create a Jupyter notebook and then record a video about what I did. So let me show you the data real quick. This is running. I see the star and the hourglass up there. So this was the source of the data. I just took a little sample initially. Now, let me ask you, is this a definition of beautiful? When you see this, don't you think this is Mona Lisa, this is just Monet style art? This is actually very ugly for me, right? But in the computer science world, it's very easy to store information in this format. This is called JSON, Java String Object Notation. So for storing data, it's very efficient to read and to write this data. For a human being to look at this and say, what is going on? Like, I couldn't even begin to comprehend, right? But again, for storing data and for reading and for writing data, this makes a whole lot of sense, okay? So that's why we use JSON strings. There's a few different formats. There's actually many, many different formats, but JSON is pretty popular. Parquet is another format that's compressed that tends to be pretty popular, especially in the big data world. It's up and coming and getting much more popular right now. So those two text files, CSVs, these are other popular ways to store data. I think the JSON stuff is one of the top storing types of data or formats of data, right? So if you go down here, it's pretty comprehensive. And I'll tell you, wait, it actually keeps going, right? Yeah, okay. So yeah, pretty massive data set. So I started to poke around here this morning and I realized, okay, basically I was just fetching the data just the normal way. Here's the JSON link right here, right? So I said, go ahead, make a request to this and then pull in the data, right? So here is the request.json. This is how this works. So basically set a couple parameters here. I want 150,000 records and I'm doing something pretty interesting. It's called basically stratified random sampling, right? It's a little bit of a tongue twister, but you're taking different strata, which are different levels or different groups of data, and you're taking random samples from each one. So the issue I ran into, like just getting access to the data is where I spent most of my time for this project right here, because I kept getting January, I got January and February, then I got 4 days of the week, but Monday was completely empty, Saturday and Sunday was gone. So that was bizarre. I was thinking, like, of all this data, why am I getting these different random chunks of data, right? So I set the request to 10 million. So at 10 million, it was running and kind of chugging along, but it couldn't complete. And I think it probably had a timeout or just stalled, or maybe just the memory got filled up and it just couldn't do it anymore, right? So I came up with a different technique, stratified random sampling, again, to get these different strata so I can get all the months of the year, all the weeks of the year and all the days of the week, because I wanted to do my analysis and see like what are these different patterns of people using the subway at different points of a time during the day, right? So you can imagine overnight during midnight, 1, 2, 3 o'clock, the ridership dips quite a bit, right? At peak hours, like the morning rush and the evening rush, it jumps up quite a bit. And you'll see some charts that depict that in just a moment here, okay? So that I knew that's what the end game should have been, right? But I kept getting these chunks of data that wouldn't help me do that type of analysis, and I had big gaps in the data. So I had to go back and come up with this technique to do the stratified random sampling, just so I can get data from these buckets and make it somewhat comprehensive, but make sure all of these categories are represented too. So the day of the week, the time of the year, the hour of the day. Otherwise, the analysis just looks bizarre and it doesn't make a whole lot of sense, right? So sometimes you have to kind of step back when you're working on these problems and think of the different approach. So there was another case, kind of similar, kind of different too, where I was working on a model one time, and it, a couple of times actually. It just took a really, really, really long time for the model to run. It took hours and hours, and I thought there's got to be a better way. So I did some research and figured out that if you use a heuristic, it's basically a representation of the data, but it's not going to be absolutely perfect and precise, but it's going to be very, very, very close, and it's going to run very quickly. So if you take a random sample and achieve your goal and you get your job done, I think that is far better than trying to fetch all the data or getting chunks of data, but you're missing big pieces of data and you have these big gaps. That doesn't make a whole lot of sense, right? You want to finish the project. You want to make it work. So if you need a heuristic and make it work fast, because you don't have days and days to wait for the model to run, or take a stratified random sample from your data and get the output you want, I think that's far superior than just giving up or just having huge gaps in your data and you're missing stuff. That doesn't make any sense, right? So sometimes you have to get clever and almost a little bit cunning in your approach to how you solve these problems, right? And figure out what the end game is, and then work backwards from there and say, I know I want to get to this point, and then figure out, okay, what do I need to do to get there, right? So that's what the exercise was about today. Stratified random sampling and a heuristic would have been a nice approach. It didn't really apply in this instance, but that's something to consider for these cases where you have long-running models, okay? So I put that in my notes down here. So we're getting all the months. You'll see that in just a minute. And we're taking equal-sized chunks. That's what this is. So 150,000 records from these months. But again, the data was so massive, I had to do that just to get this thing done and just to be able to answer the questions that I wanted to answer, okay? So we're taking chunks. So it does look a little bit gamey, and it does look like, okay, we have 150,000 from March and from May and from December. But guys, that was the only way that this was going to happen, okay? Otherwise, the data set is just too massive. You saw it. It's this thing over here. It's this beautiful looking creature over here. So sometimes you just have to get creative in your approach. So I think this is almost done. It's looping through all these strata and getting the data 12.1 to 1.1. So I think it's almost done. We're going through the entire year of 2023. Okay, so I think this is representative. If you have these weird years like 2020, we had COVID. Is that really what you want to analyze? COVID? Maybe, maybe not. I just wanted to take like a normal sample of data. So I think the entire entire year of 23 is fine. I think that's a good sample or a good starting point. And again, we're working with samples of data just to make this thing work. Okay, so hopefully this is done. I've got some notes down here about what I was doing just above. Okay, and the first time I started way too small. I only had 15,000 records and it wasn't enough. And like I would have to see even, I don't even know how many people ride the subway, millions every day, right? Let me check this out. This is why this data set is so massive. How many people subway daily? Okay, that's a change on the weekends versus weekdays. 3.6 million daily riders. Okay, so that's a lot. And they're capturing all the information from all these riders. So probably twice. You're probably taking it to work and home from work, maybe 3 or 4 times if you're running errands or going to the gym, right? So to capture, wait, what was I already forgot? 3.6 million, probably twice a day or more, and collecting all of that for all of 2023. So that's a lot of riders. Let me do one more quick analysis here. Calculator. Now this is very, very general, okay? But let's just say 3.6 million, 3,600,000 times, I'm going to just go out on the limb and say 2, okay, times 365, very general because it's going to fluctuate during the summer. Oops, go back, clear. I'll clear the whole thing, right? 365 times 360,000 times 2. So 2.6 billion records per year, just general, right? Just generalizing. And that's only for 1 year. So I don't even know how far back in time this goes. If I look at this is 2024. So that's the most recent that they have here. I guess they didn't collect 2025. And it goes back here to 2024. And this is not sorted in any specific order too. So these years are going to be all over the place. Anyways, the point is massive, massive, massive data set. So you have to get creative with how you work on this stuff. Okay. So the data comes in. That's fine. This is my data frame here. So I'm looking at transit timestamp, transit mode, subway. I think they're all going to be subway. I don't even know why they have a category. This is station ID, station complex. So that's the name. And then the borough, payment method, MetroCard or Omni, and then fare class, full. I think they have different classes like student class, ridership. So this is a number of people that went through this station in 1 minute. I think that's how you interpret that on that date. Okay. Then you have number of transfers. That's probably going to a bus, lat long coordinates. So that's helpful too. And then georeference. Okay. So that's it. Basically, it's the counts of the riders on the subway over a period of time. So that's what we're looking at. So I took the data, okay, transformed it into something that's a little bit easier to work with. So I have a couple things I'm doing over here. I'm getting the hour, day of the week, and month, because that doesn't come very easy to work with, right? So I have to parse that out from there. That's the year. This is the month. And then what? 0101. Okay, so January 1st, 2023, and this is the time. So that's how they're doing it, right? So I want to get the time, the day of the week, and the month of the year. So this is called feature engineering. I'm basically just parsing out from that timestamp right there that has all kinds of details. I just want to chop it up and make it a little bit easier to work with. So I have hour, day, and then month, and then making sure that this is actually a real timestamp, okay? And then looking by riders by hour. So we're doing a group by hour, and then summing all these, right? So we get the comprehensive number of customers that go through each station by hour, right? So again, the time of the day, I think they give it to us per minute, but we're collecting it, we're aggregating that up into hours. And then since they don't give us the month, really, they don't give you a whole lot. All they give you is this thing over here, right? So 2023 0101. So we have to get the year, month, and day out of that. So that's what this is all for. So now we have these new features over here on the right. This is called feature engineering. And I have the hour of the day of the week, and the month of the year. So I think that's a little bit easier to work with versus what they gave us, right? So now I can create my first chart. I'm going to look at the ridership counts by hour of the day. So pretty straightforward. I get the riders by hour, right, doing the aggregation that I had above. So, let me expand this too. So I did create a couple data frames over here. So the original data frame is this right here. This is data frame.head, and I printed a little separator over here. That's all it is. Then they have riders by hour. Okay, so you go down here, ridership by hour. So you have 0 through 23. They're using military time here. And the ridership counts. You can see it goes down at 3 and 4 o'clock in the morning. That totally makes sense. And then we have by day of the week, and then again the counts of everything, or the sum of everything. And then by month. So we have everything laid out, but it's not plotted for us. So I want to create a plot so it's just easier to visualize, because if I look at this, or if I give this to any stakeholder, they're really not going to know what to do with it, right? They probably put that into Excel and try to plot it or something. Same thing with this. Like it tells a story, right? And this is all correct. I'm sure it's correct, and I'm sure it's interesting. But when you look at these plots, it's just a lot more rich. It's a lot more meaningful, right? When you create the chart, it has to answer questions if it generates a whole bunch of questions, it's not a very good chart. If people look at the chart and say, oh, yes, this makes sense to me, and I understand, this is a great visual, that's a good chart, right? You want to answer questions, not create questions. So I'm basically getting the hour sorted. So we're doing sort values, so it's sorting in descending order. And I have the original data frame that's called riders by hour. If I do Control F, paste that over there, you'll see that. So here's the original data frame up here, rider by hour. That's how we got this right here, right? And then I'm just recycling that or reusing that to get my chart down here, and I'm sorting it in order because a lot of times, most of the time, it doesn't come just naturally sorted in order from 0 to 2300 hours. Normally, you would have to convert that yourself. I mean, it could randomly work out like that, but usually it doesn't. And if you rerun it another time, it probably wouldn't be in the order that you want, right? So you kind of want to force these things to follow some kind of pattern that's coherent and consistent. I guess sip of water here. Okay, so the chart is running. The code is running. It's building the chart. Honestly, it's a little bit slower than I thought because I was testing this code before I turned on the recorder, but I'll just let it go. Basically, again, this is sorting the data frame. This is doing the sort over here, right? And Control F, if I put that in, you can see we're just creating categorical codes. So for 24 hours, 0 to 24, where that's the range, 0 to 24. Then we sort the list over here, and then we use that object. This is a data frame object, plot hour on the x-axis and ridership on the y-axis. Okay, so now we got our chart. Let me run the next one because that could take a couple of minutes, and I'll run the next one after that. Oh, that one's already done? Well, that was fast. Okay, so for some reason, the first one took 5 minutes, and the second one took 1 second. But anyways, we have what we need here. So you can see ridership dips down overnight, 470 riders. 470,000. Okay. Yeah, for a second, I think it's a little bit higher. 269K. 3 o'clock, we hit the nadir or the low point, 219K, and then it kind of spikes up a little bit. So people are getting ready, I guess, hopping on the subway, going to work at 4 a.m. Maybe essential workers. 5, 6, 7, 8. This is 9, 8 o'clock. So the ridership is at its peak, 6.4. And then this is 9 o'clock. So most people are at the office. And most people are where they need to be. You have some people come in a little bit late. Maybe at this point they're running errands, going to the doctor, or whatever it is that people need to do. Now we're at 2 p.m. This is 3, 4, 5. So here's the peak. 1700 is 5 p.m. And I kind of hard to read that. 7.1 million. And this is 6.4 million. So here's the peak. 5 p.m. 6, 7. 8 is 2000, 9, 10, and this is 11 p.m. And we still have 1.25 million people on the subway at 11 p.m. Okay, so that is a normal day on the New York subway. So this is by day of the week. So Monday, Tuesday, again, I'm doing the sort. So I'm creating categorical codes over here and then sorting everything. So ordered equals true, and then using that data frame. So this is riders by day. This is riders by hour. So different object, different data frame, right? So feeding in different slice of data. So we have Monday, Tuesday, Wednesday. There's a big spike up here, 15.36 million on a typical Wednesday. Now remember, this is for the whole. This was what the whole year of 2023. Okay, so we saw over here. On any given day, there's about 3.6 million people on the subway. So it's 15 million. Can sound a little bit high, but that is over the course of 2023. Remember, that's how we fetch this data. So Thursday, again, pretty high, equal to Wednesday. Tuesday is a little bit lower. And I'll be honest with you, I think there wasn't like a big dip on Tuesday because I did that random stratified sampling because that was the only way I could get this to work. It just happened to miss some Tuesdays in there because I would expect like Monday, Tuesday, Wednesday, Thursday, Friday to be somewhat consistent. I can definitely see lower ridership on the weekends. People aren't going to the office, right? They're doing recreation activities, going out to Central Park or going to play or running errands or whatever. So I would expect a dip on Saturday and Sunday. This totally makes sense. This Tuesday, I think it's an issue with the random sampling. But again, I had to use that technique where I would have no charts, no video, and no analysis here, right? That was the only way to get it working. So again, I think Monday through Friday is going to be pretty consistent. You could see some work from home Monday and Friday, right? So those might be a little bit lower. Wednesday, Thursday totally makes sense. Tuesday, I'm guessing it's the randomness. And we just didn't happen to pick up as many records for Tuesday as would have been nice, but that's fine. It is what it is. So here's January again for all 2023. So 4.4 million people. February spikes up a little bit, almost double. March kind of similar to February. April, there's a little dip. May, June, July. Now in July, people are out of town, going on vacation, so ridership dips. I think that's what that is. And that's it. So that is ridership by month for 2023. Now I want to look at the top most frequently used stations based on number of swipes. Remember, we're counting all the people that go through all the turnstiles, and we have the station ID and the station name. That was in the original data set. So these are the top 10 stations. We're getting the N largest. Okay. And again, this is station complex. That's the station name. And we're doing the group by ridership. So I already knew this one. Times Square. So 2.9. Wait, is it 2.9 or 29? 1, 2, 3. Yeah, 2.9 million for 2023. There's no other filters or anything applied here. Grand Central is close. It's not that close. It's off by 1 million, but that's number 2. And Herald Square is number 3. Union Square, that's a big one, 14. And the top 10 rounds off with 74 in Broadway. So that is, I think, that's Jackson Heights. Yeah, so they made it to the top 10. Wow, I didn't expect that. But all these others, these other 9, I could have guessed that pretty easily, but I didn't know that this would make it to the top 10. Here's the bottom 10. Broad Channel, Beach 105, Beach, Aqueduct, Racetrack. I think I know what that is. And Beach 90. I don't even really recognize any of these. So these are not places I would go. I think this is on the A line maybe, and it's pretty far out, Far Rockaway or something like that. So anyways, I thought that analysis was pretty interesting. Now let's create a heat map so we can visually see what's going on here. Okay, so I always say a picture is worth 1,000 words. If you take a visual and show it to somebody and they can understand quickly and easily what's happening, like these bar charts over here, that makes sense to me. Okay, all this makes sense. Then I don't have to spend 1,000 words to explain what's going on. I can have a very short conversation with someone, give them a printout, or just share my screen with the person because they're looking at a plot or some kind of chart, and they can visually see how everything works out. Okay, so here we have a heat map. If I zoom in on this heat map a little bit, you can see there's a lot of concentration of subway usage. Over here, this is going to be Times Square. Okay, they give us the lat long coordinates. And this is going to be, I think, Grand Central. Yep, that's Grand Central. I can recognize that. So these are the 2 that we just saw are the 2 top most frequent. And what was number 3? No, over here, number 3 was 34 Herald Square. Okay, so let's look for that one. So this is the corner of Grand Central, so that makes sense. And then 34th Street, Herald Square, that is right over here. So that's number 3. So that's the top 3 plotted in a heat map. So I think those are pretty useful. Now let's look at another map over here. This is a cluster heat map. So a normal heat map is great for visualizing values in a matrix, like a matrix rendering or some type of color intensity. The purpose is to show patterns, trends, and magnitudes in the data, and rows and columns stay in the original order. We're just showing like what's the concentration of the data that we're looking at here. This is people going in and out of different subway stations. And it's used for correlation analysis, traffic volumes, and activity levels. So it's working perfect for us over here. So a clustered heat map is a little bit different. A clustered heat map not only shows the heat map, but it reorders all the rows and columns based on some type of hierarchical clustering. Okay, so it takes a small mathematical calculation and looks at the difference, or the difference between 2 data points. And the less the difference, the closer they are. So those will match up and those will end up in the same cluster. If it's too far apart, then those will get reoriented into another cluster that's homogeneous with the other items in that cluster, right? So all the clusters in the whole data set, if you're assigned to a different cluster, they're heterogeneous. If everything is clustered in the same cluster, then it's homogeneous, right? So let's zoom in here and check out this map. And again, the cluster heat map not only shows a heat map, but it reorients the columns and rows based on like that mathematical expression I just explained to you. So the purpose is to reveal structure about natural groupings in the data. This applies to algorithms like Ward or average, and groups items that are similar together, right? And this can be a dendrogram. That is one type of hierarchical clustering. And there's a few different approaches to try to solve this problem. I think there's like 8 or 9 different types of clustering methodologies. So you can see here, everything that's cluster 7 is midtown. So this has high concentration over here. And again, what are we basing the clustering on? Latitude and longitude, right? So how close these subway stations are together. So you can create the clusters a bunch of different ways. The counts of the frequencies of people going into the subway or using those subway stations, or the lat-long coordinates of the subway station and where they're located. So that's how I did this. So you can see everything is orange is together, everything that's blue is together. That makes sense. Here you see some yellow out here. This is cluster 18. So geographically, these are closer together, right? This is cluster 12, and over here we have cluster 12. So Upper East Side, Upper West Side, and over here we're getting out of Manhattan. Now we're into, I think this is Bronx over here, right? So this is cluster 6, and this is cluster 6. So geographically, all these items are clustered similarly together, okay? So, and then I did one more test. So basically, testing 1, let me change this to 1. 1 just didn't work out at all. I actually deleted it. Okay, so I want to look at, just make sure that this is the right format. So I want to make sure everything is numeric. Ridership should be a number. Sometimes these things come in as labeled data. So if you see that, you have to convert that to an actual number. So I thought, let me look at some type of anomaly detection to see if there's anything in the counts of the ridership that could be anomalous or different in different types of scenarios, right? So an anomaly is an outlier. I was just curious to see, are there some outlier events here? Is there something that throughout 2023 looked weird? Was there some type of event that was different from most of the other events? So that's what this anomaly detection does for us. It helps us look for things that are unique and unusual and just doesn't fit the pattern of the entire group. So I did the isolation forest. I have a couple videos on my website about how that works. That's a very interesting technique to find these outliers. And I plotted the results over here, and I just found one single outlier, January 3rd, 2023. And I didn't like how this chart spikes and moves around and bounces around. It's very erratic and very, very bouncy. But it is what it is. All right, we're trying to do anomaly detection. I didn't find any anomalies. I was thinking of deleting this whole thing and not even putting it into the video, but then I thought I'd leave it just to showcase. Like sometimes you'll run experiments, it doesn't really work out, and that's fine. You try these things and you see what works and you use what works. And if it doesn't work, that's fine. You move on and you try something else, right? You try different experiments. That's why it's called data science. We run experiments, and you'll never know before you run the experiment what the outcome is going to be. That's impossible to know, right? You run the experiment, and based on the outcome, then you determine, does that match my hypothesis? So the hypothesis is an estimated guess. You'll say, I think this is the outcome that we're going to see. I feel like the data is going to say this. I believe we'll see this when we look at the final report, right? So you run the analysis, you do your experiment, then you see if the results of the experiment match your hypothesis. If it does, that's great. Then you've proved your point. If it doesn't, you have to reform or reorient your hypothesis. You can't change the data to match your hypothesis. That's insane, right? You create a hypothesis, run the experiment. That's the data science. If it matches your hypothesis, great. If it doesn't, then reform your hypothesis, right? Or run some more experiments or try something else to get creative, become innovative, right? And just try different things. So that's what data science is all about. Just trying different ideas, testing those ideas, and seeing what the outcome is. So that's it. Hopefully this was useful and helpful. I try to make all the videos practical and, just give you different demos of what you can do with data science and different techniques that can be applied. So I think this stuff is pretty interesting, and hopefully you find it interesting as well. Okay, so I introduced a few different concepts here and a couple different topics. So I think we beat this horse to death. I'm going to wrap it up here. I'm going to share all this code with you. So I'm going to download this as an HTML file, and I will post the code. I post the video a little bit later today. So you'll have all this code and you can run it for yourself and test the functionality of everything and hopefully learn from it, right? I share all the code that I have here with other people to drop knowledge and just to, share something that I think is interesting with other people. So collectively, everybody can learn together, okay? So that's pretty much it. I'm going to wrap it up, and I will see you guys in the next video. Bye for now.